This is a traditional proof of the fundamental theorem of calculus. Hard to follow, big symbols, largely unhelpful. Today we're going to break down the fundamental theorem by 1. Understanding the derivative, 2. Posing the question of finding the area under a curve, and 3. Taking advantage of some intriguing relationships. Let's start off with a line. For many of us, lines are the first graphs we learn about in our transition from a number line to the two-dimensional world of the Cartesian plane. The defining property of a line is that it has a constant slope, meaning that every x I go to the right, I have to go a specific y amount. Now, lines are fascinating pieces of geometry, and there's a lot of interesting math that can go behind them, but in many scenarios they are very useful. In some applications, we need to utilize curves, quadratics, cubics, exponentials, or maybe even the occasional trig function. Luckily, many of the curves you will encounter are differentiable. Essentially, if you zoom into the curve enough, it'll start to look like a line. If you don't believe me, you can go on over to Desmos, graph curve, and just start zooming in. In the case of this parabola, after a few dozen clicks, it's definitely starting to resemble a line. But what does this actually mean? Well, you can imagine that differentiable curves can really be viewed as a sequence of lines with varying slopes. Take the example of these tangent lines tracing out a parabola. Or put another way, you can imagine that these curves have a rolling tangent that pushes itself along the curve. Now, I'm not a mathematical historian, but I imagine that this observation prompted the idea of a derivative. Essentially, it's a function that maps the slopes of these tangent lines. Some tiny difference in y we'll call dy, over some tiny difference in x we'll call dx. But what does this parent function have to do with the area under its derivative? Well, a reasonable start is to figure out how to approximate the area under the derivative curve in blue. Luckily, we can accomplish that by using rectangles. Let's say, for now, 1 for every increment in the x direction. What's interesting here is that as we add more and more rectangles, the widths, we'll call dx, decreases rapidly. Even more impressive is that the area under the derivative curve, as well as the parent function's tangent, gets more and more accurate. Now, the area of each of these thin rectangles can be thought of as the length multiplied by the width, while the height is the y value of the derivative, or the tangent slope of the red parent curve, some df of x over dx, and the width is also dx. In effect, the area of each rectangle is whatever df of x is at that given point. Now that we have a sense of where we're headed, we can go ahead and clear up the graphs. Since we're looking at values of df of x, it makes sense to view them in their most natural form, as a y component of incredibly small slope triangles. To find the area under the derivative curve, let's say from a to b, we need to add up all of these df of x values. Well, by simply sliding all of these slope triangles across, we find that the sum has to be f of b minus f of a. And that's the fundamental theorem of calculus.